Hello everybody to my presentation. So my name is Hansche and I'm working at the University of Graz. And I'm going to present to you basically my master thesis, which is about temperature inversions on Amazalik Island. But this will be explained in more detail a bit later. First, I would like to introduce the Interact station where we conducted this study. Here on the left side, you can see an overview of the Interact field sites in Greenland. And here at the red dot is the station where we conducted our study, so at the Sermelik station. And this is the place where we spent approximately 14 days. And where we collected heaps of data. So, and here we can see the research area and the location of the station. And the whole location is located in the lower Arctic zone. And one main reason why there is a station is the Mitivakat Glacier, which is close by. Here you can see a nice picture of one of Mitivakat's tanks. And already in the 1930s, or to be more precise, in 1933, an expedition led by the famous polar researcher Knud Rasmussen went to the Mitivakat area to collect glaciological and geomorphological data about this area. They took, for example, pictures. They also mapped the terminus of the glacier, and they also did ablation measurements, and they are among the first conducted in Greenland. So this is quite impressive. And to give you an idea how the environment changed since the expedition, I would like to show you two pictures. Here we can see a picture from one of the expedition members, the geologist Milters did this picture in 1933. And we can see the glacier terminus of Mitivakat. And here, the same photo position in 2010. And we can clearly see how the glacier retreated from there. Yeah, and since 1970, Sermelik is a permanent field station, and it was especially established to provide a logistic base for the ongoing glaciological and hydrological and geomorphological investigations. And here, just to give you an idea, a few studies conducted in this area, and there are many more out there. Yeah. So we went there to study temperature inversions, and this is a situation in which the temperature increases with height. So under normal condition, the temperature is decreasing with height, like we see here in the graph. So here we have the temperature, and here we have the height, and here we can see how the temperature is decreasing. But something quite different happens quite often in the Arctic. The temperature is increasing with height. And this is called a temperature inversion. So let's look at this graph here. Here we have the air temperature, and here we have the height. And here we can see the decrease and suddenly the increase. And this is the temperature inversion. And this condition has, of course, multiple consequences for the Arctic environment. For example, it has an influence on the vertical gradient of flora and fauna, but also on snow cover or glacier retreat, and many more. To understand this impact a bit better, and also why it's important to improve our knowledge about this condition, I would like to give one example. Because at the beginning of this presentation, I told you a bit about the expedition in 1933, where they collected one of the first ablation measurements in Greenland. And one study, it is Hasselt et al., we can see it here on the left side, compared these historical ablation data with more recent one. And they discovered that the ablation is much higher than in 1933. Now you can think, oh, this is not really a surprise, climate change and so on. It has to be more in recent days. But it is important to know that 1933 was an especially warm summer in a warm period, with summers who were ranking amongst the warmest during the 20th century. And one reason why the ablation rate is still higher in the recent years than in 1933 is that the glacier retreated out of the cold maritime inversion layer. So I will try to explain it a bit more. Let's look at this graph here. Here 0 indicates the station Sermelik, and here is the distance from Sermelik. On the y-axis, we see the height above ground. The brown area indicates the Mittiwakaat Valley, and the light blue area is the glacier. And this is the atmosphere, the air temperature. The blue colors indicate a cold temperature, and the red colors indicate a warm temperature. And when I talk about the cold maritime inversion layer, I'm talking basically about this area here. So it's the cold air coming from the sea, and it can reach far into the Mittiwakaat Valley. And this is approximately the place where the glacier is today. So it's not really in the maritime inversion layer, but if we look at the position of the glacier in 1933, we see that the glacier was during this time in this cold maritime inversion layer. And of course, this had an influence and creates less ablation rates, although the summers were really hot and there was a warm period. So, and for this reason, it is important to develop our knowledge about the spatial and temporal variability of temperature inversions. And exactly this is what our objective was for our area of interest. We wanted to know more about the inversion characteristics, and what I mean with inversion characteristics will be explained soon, and variability above different surface types like rock or sand, and also during weather shifts. Another aim was to compare our data to radiosonde and reanalysis data, because these data are widely used to study temperature inversions, not just in the Arctic, but also in the Arctic. But I'm not going to talk about this in this presentation because it is not enough time. Yeah, but in order to study the temperature inversions, we collected profiles of atmospheric variables such as air temperature, humidity, or pressure. And these profiles were collected with drones. Here in the lower right corner, you can see the drone. And the sensor was mounted above the camera. You can see here the sensor. And so we flew from 0 meters above ground levels to 120 meters above ground level. And the drone was controlled with the smartphone. And just to give you an idea how this navigation system looks like, here in the upper right corner is a screenshot of the smartphone. Yeah. And here's our research area. And here's again the station Sermelik. And the dashed line was our walking path. And the points where we collected the profiles are indicated with letters A to H. And the profiles, we took the profiles always on the same points, of course. We also used a weather station transect. For example, here, weather station in Sermelik, which was 7 meters above sea level. And the one which is called Sissimor was established by us during the field campaign. And here's a picture of our weather station. So the points where we took the profiles were above different surfaces and settings. For example, if we look at point A, it was at the station Sermelik, above rock and sand and close to the sea. E was at the beginning of the Mitiwakat Valley and above sand. C was at the end of the Mitiwakat Valley and also above sand. E was in front of the glacier, above sand. E was at the glacier tongue, above melting ice. And F and G was above the glacier, so above snow and ice. And H was on a nunatak, so above sand and rock. And altogether, we collected 147 profiles in just 12 days, which was quite a lot. So we had long working days from 8 in the morning to 10 in the evening. But it was also a lot of fun. And some of these profiles were collected simultaneously, like here, B and C. So B was at the beginning again of the Mitiwakat Valley, C at the end. So one was standing at B, the other one at C, and we took the profiles at the same time. And the same for D and E. So, but this was not enough. We also collected water level and water temperature data from a proglacial lake. You can see the lake here. It was between the position D and E. And we also collected water level data from a proglacial river here. Yeah, furthermore, we used the radiosonde data from the nearby station Tasselak. It's approximately 10 to 15 kilometers away. And the idea was to compare the twice daily soundings at 0 and 12 UTC from the radiosonde with simultaneously collected drone profiles at the station Sermelik in order to detect how well the radiosonde data resolved atmospheric stratification. And we did the same for reanalysis data, so for ERA interim data and ERA 5 data. Yeah, and we were interested to quantify the different inversion characteristics. For example, the inversion base, this is where the inversion starts, so where the temperature increases, or the inversion top, it's the end of the inversion, where the temperature is starting to decrease again. The inversion thickness, the inversion magnitude, which is basically the temperature difference inside the inversion layer. We were also interested in the inversion frequency, so how often do we observe inversions? And if so, what type is it? Because there are two types. We have the elevated inversion, where the inversion layer is elevated, as the name says. So first the decrease and then the increase. And we have the surface-based inversion, so where we have an increase in temperature already at the surface. Yeah, so let's look at some results. We observed temperature inversions in all our profiles, and we observed more elevated inversions than surface-based inversions. So let's look at this one here. So 206 elevated inversions and just 48 surface-based inversions. And based on our observations, we developed a conceptual model with the main inversion characteristics. You can see it here. So just a short introduction to this picture. So here we have the sea. This again is the Mitiwakat Valley, and this is the glacier. Here again the distance away from Sermelik and the positions where we took the profiles. The black bars indicate the inversion. Here above, we can see the main wind directions we observed from the weather station and in the field. So every day we have a sea breeze, which is picking up over the day. And the sea breeze is reaching far into the valley. And on the glacier, we observed a katabatic wind, of course. Yeah, and the profiles close to the sea showed mainly elevated inversions. It's because of the influence from the sea. It's because of the sea breeze, because the sea breeze brings the cold air into the valley and pushes up the warm air. So we have the elevated inversions here. And on the glacier, we observed mainly surface-based inversions. It is because of the glacier cooling, because ice or snow cannot be warmer than 0 degrees Celsius, so we have a decrease on the glacier increase on the glacier temperature. And this is also what we see here. So a short introduction. Here are the positions again, A to H. Here's the reminder, so what surface it is. And here we can see the fraction of the inversion type we observed above the position. Blue indicates the elevated inversion, the fraction of the elevated inversion. And the red ones, they're indicating the fraction of the surface-based inversion. And as I told you before, the positions close to the sea or above rock or sand show mainly elevated inversion, while the positions on the glacier show a high fraction also on the surface-based inversion. And I would like to emphasize especially D and E, because D is in both are collected simultaneously, and they are both on 150 meters above sea level. D is just above sand and rock, and E is on ice, and we can clearly see the difference. Okay, then let's move to the weather shifts. We were quite lucky because we observed two major weather shifts during the field campaign. One cold front, you can see here the drop in temperature, and one warm front. Here you can see the rise in temperature. And also the wind speed is picking up during the fronts, especially in the higher elevations. Yeah, so I will shortly introduce the picture here. So here again, we have the distance from Semmelik and the positions where we took the profiles. Here again, meter above ground level. Then the size of the circle, they indicate the wind speed. So the bigger there are, the more wind speed there is. And the arrow indicates the wind direction. And here we can see the different layers of the atmosphere and the temperature. Yeah, and during the cold front, the warm air is getting pushed up, and this creates strong elevated inversions with a high magnitude. And while the cold front passes, the sea breeze is peaking up. And this condition creates a mixed unstable layer below a stable layer. And as soon as the cold front is reaching the higher elevations, so the weather station Sissimore, the wind speed is picking up to one of the highest during the field campaign. And this, of course, encouraged the development of a mixed low boundary layer with really weak inversions. So here we are at the beginning of the cold front, and here we are at the end of the cold front, and you clearly see the temperature difference of the air. So after the cold front passed, the wind decreases at higher elevations, but the sea breeze is picking up. You can see how the sea breeze is picking up over the day. And this creates, despite the cold air, elevated inversions. They are a bit weaker and shallower, but they developed. So then to the warm front, here we have the same kind of pictures. Here is the beginning of the warm front, and here is the end of the warm front. So while the warm front passes, the air temperature is rising first in the higher elevations. And we can still observe a moderate sea breeze here, which again creates elevated inversions. And over the day, the wind speed at higher elevations is picking up, while in the lower area, the wind calms down. This cold, strong wind pushes then down the warm, stable layer, and this again creates quite strong elevated inversions with high magnitudes. So, and on the 16th, the warm front passed already, and the cold air at the ground is eroded and replaced by warm air. You can see here the big temperature difference. And this leads together with a really, really weak sea breeze. If you look here at the small circles, to really thin and weak inversions. So, and the the effect of the warm front is also observable in our water level data and water temperature data. We can see here a clear rise in the water temperature, and also the water level is rising quite a lot. Okay, so then to the conclusions. So we mainly observe elevated inversions at the positions close to the sea or above rock and sand. And we observe, not mainly, but we observe surface-based inversions at positions on the glacier. This is due to the cooling of the glacier surface. And the inversion base height varies during the observation period. So there's not one base, it varies a lot. And the influence of the sea reaches far into the Mitiwaka Valley. And when it comes to the radiosonde is able to resolve the general pattern of the atmospheric temperature profile, especially in higher elevation bands. They are quite, they show a high similarity, but they also show a high deviation in the lowest 100 meters above sea level. And when we look at the era interim data, or when we compare our drone data to the era interim data, we observe that the era interim data show a high deviation from the drone data, while the era 5 data show less deviation and a higher linear relationship. Yeah. So then I would like to thank you for your attention, and I really want to thank the Copenhagen University for establishing this awesome station in Sermelik. You can see a lot of passion and effort in every corner. And I also would like to thank Interact for the support. Thanks a lot.